Good morning. My name is Lindsey Penet, and I'm a senior civil engineering major at Clarkson University in Potsdam, New York. And I have been working under Dr. Robert Thomas in our concrete lab. This research analyzes the feasibility of the use of electric arc furnace slag as a supplementary concrete coarse aggregate. So today I would like to discuss the motivation behind and some background of this project. I'll discuss the expansion tests that were conducted as well as the results of these tests. I will also discuss how this material was found to affect the mechanical strength and mechanical properties of concrete, and then I will discuss what impacts these results may have on the concrete industry. So electric arc furnace, or EAF slag, is a rock-like material that forms as a byproduct of the steel recycling process. And more than 10 million tons of this material are produced in the United States per year. And unlike blast furnace slag, which is commonly used as a supplementary cementitious material, the majority of EAF slag ends up as waste, and it will cost steel manufacturers anywhere from $60 to $80 per ton to dispose of this material. And this is both economically inefficient and poses a sustainability issue. If the EAF slag is able to be applied as a supplementary coarse aggregate, not only will this reduce the disposal costs and the landfill burdens, but it may also have effects that improve various concrete properties. So the main concern regarding the application of EAF slag as a coarse aggregate is its potential for expansion due to the hydration of the free calcium oxide and free magnesium oxide that make up a large percentage of the EAF slag's composition. While hydration is, of course, a fundamental reaction in cement chemistry, if too much expansion of the aggregates results, it could lead to tensile stresses on the concrete, leading to undesirable cracking, which, of course, can affect the structural integrity of our concrete mixes. Therefore, we found that the replacement levels end up being limited mainly by this expansion. So the main tests that were completed during this research were ASTM D4792, which is the standard test method for the potential expansion of aggregates from hydration reactions. And this test measures the volume expansion of dense graded compacted aggregates. Samples for this test were prepared using a modified California bearing ratio test, which had to be modified for use with coarse aggregate as opposed to the traditional finer soils. This test was performed on samples of 100% traditional limestone coarse aggregate, as well as samples of limestone aggregate supplemented with 10, 20, 30, and 40% electric arc furnace slag by volume. On the right, you can see a photo of the final experimental setup with the compacted aggregates under a surcharge weight of 10 pounds, and the dial gauge is how we measured the expansion of the aggregate. These samples were kept submerged in water at 70 degrees Celsius for the week-long duration of the test. And expansion readings were recorded daily at approximately the same time. And on the graph on the left, you can see the expansion over the duration of the test for the 5 mixes. And as expected, we saw the aggregate expand as the test went on, more so as we increased the replacement level of the slag. As to be expected. But as you can see, our expansion over 7 days did not go above 0.07%. And according to the majority of literature, the limit on aggregate expansion in concrete ranges from 0.08% to 0.1%. So this falls even at the replacement level of 40% below this threshold, meaning it could be a viable supplementary coarse aggregate. So we also looked at some mechanical properties of concrete with the use of the slag aggregate. We did these tests with a base mix with traditional limestone aggregate, as well as mixes with 30% and 40% replacement, as the higher replacements would be the best economically and sustainably. So we saw that there were small changes in the compressive strength of the EAF slag aggregate concrete, as well as a decrease in the modulus of elasticity, which is hypothesized to be due to the more porous nature of the EAF slag when compared to traditional limestone aggregate. And from this testing, we wondered if this decrease in modulus of elasticity may cause a decrease in flexural strength, which of course would mean that the material does not have any positive impacts on concrete. So we performed flexural strength tests. We did simple beam tests with center loading to test our flexural strength, and we actually found that there is a moderate increase in flexural strength in the beams using EAF slag aggregate, which was a very interesting development. And then just to briefly discuss how this could impact the concrete industry going forward. First of all, cost. Traditional limestone aggregate is often cost anywhere from $10 to $50 per ton, which of course may vary based on location, demand, and availability of the aggregates. While EAF slag will cost anywhere from $5 to $10 per ton to be used as coarse aggregate, which of course is a decrease in cost. And as for potential uses, we believe the main application of electric arc furnace slag aggregates could be in more flexible concrete pavements due to the previously mentioned lower modulus of elasticity, which could allow for concrete pavements to be used more in areas where freeze-thaw damage is more of an issue, which the added flexibility will add to that. And as well, using this material as a coarse aggregate will introduce a use for it that is meaningful and has positive impacts and is not just being disposed of and creating the environmental issues. And overall, these slag aggregates can have both economic and engineering benefits to our concrete industry.